Okay, so welcome everybody. We have today Amine Asselah from Paris. He will talk about intersection of two independent random walks in ZD for large D bigger or equal than 5. Amine, please.
So thanks a lot, Pablo and the organizers for the invitation. So it's a pleasure, and I'm going to tell you about some work that I like, and this is why it's a little bit old. It's 2 years old, and it's done with B.Schapira. But it's the conclusion of many years of research. So I would like to present a few ideas. And so the problem also is very simple. Everybody understands it right away. So let me start with notations. So I'm going to first just call a random walk Sn. So n is actually the time. And my random walk Sn is going to be on the sides of ZD as usual. And most of the time, I'm going to take D larger or equal to 5. That's my first random walk, and I hope everybody knows about that. That's the most simple process in probability. And then from the random walk, so it starts, let's say, at 0, it moves, let me change color, it moves on the lattice. And you have something called the range, which is also a very well studied process. So this is the number or the set of sites visited up to time n. And I'm going to stop it, let's say, at n minus 1, just to have n sites. And I might use a language of polymer. I'm thinking of this as a polymer made of n monomers. So the positions are the positions of the monomers. So this is the trace of the random walk, which I might also call the range. Okay. And R infinity is going to be the whole trace of the random walk in an infinite time horizon. Okay. So it's all the Sn for all the integers. So I take now a second independent random walk. I call it S tilde n. So this is my copy, independent copy of Sn. And the question I'm interested in is just to have the intersection of those two sets in infinite time horizon large. And the real question is how the two random walk organized to have this thing large, bigger than something. That's the question. So I want to estimate the tail of this event, or as t goes to infinity, and the scenarios. And this makes sense only in dimension large or equal to 5, just because when you take the expected value of this intersection, this is finite only in dimension 5 and more. So let me just do the simple computation so that everybody is convinced. So the expectation with respect to my two randomness of this intersection, you can write it as the set of all the sites in ZD that are visited by the two walks. So probability that you hit Z, and then you square this thing because you have your two independent random walk. Okay, so that's it, exact. And then it's simpler to write it in terms of the green function. That's a way for me to introduce green function. Green function is the number of visits of site Z when you start, let's say, at 0. So this is always less, the probability of visiting is less than the number of visits. And you don't forget to square it. And so the only thing you need to follow the whole talk is the green function. That's green function, Green's function asymptotics. And that's the only thing I know about green function, that it decays like D minus 2. Okay, so the number of visits of a site at a distance r is 1 over r to the d minus 2. And therefore, the nature of this series is the same as if you sum this thing. So it's you sum an r d minus 2 square, and there is a volume element of this type. So this is finite if and only if d is bigger than 4. So this is equivalent to d bigger than 4. So you need to wait until dimension 5 and more so that the typical number of intersection is finite. And therefore the question makes sense. Okay, so if you have any question, I'm not seeing the discussion, but if you have any question, just either you send me a chat or you just speak. Okay. Let me tell you, since I was saying that this is a well-studied object, this question is also an old question, so it was more, let's say, fashionable in the 90s and so let me first say that in 93, so let me say about the literature. There is a study of Hanin, Mazel, Schlossman, maybe 2N, I don't know, and Sinai, where they obtain the tail up to some, I mean, you'll see what, let me give a name to this intersection as I intersection up to infinite time, bigger than t. They could show that this is basically exponential minus, they don't have the constant, but they discovered this exponent with a plus or minus epsilon. So they are missing the exponent by an epsilon. So for any positive epsilon, they can show that as t goes to infinity, that's the scaling. Okay, so the key thing is that they discovered this one minus 2 over the exponent. And this came as a surprise, actually. And in their paper, they say that this was observed already in the 90s by Harry Kesten. So they make a small remark like that this was already seen, but they present a short proof, very elegant proof in moment computations, and a lower bound with finding a scenario. So, but, well, there was this plus or minus epsilon that for some time people tried to reduce to 0. And the first, let's say, step in this direction was in 2000, maybe 2001, by Bolthausen, Michel van den Berg, and Frank and Hollander. They have like 2 papers actually about the same topic. This one is really about the intersection of 2 independent Wiener sausage, but I'm going to write it in terms of this intersection of random walk. So BT, so they do not take an infinite time horizon, but just a large time. Intersection with B T again for a copy, and they ask the same question. And they say that they are motivated by, so let me also put that I'm really taking an average with respect to the 2 randomness. And motivated by Hanin and company problem, they obtain a large deviation principle with the constant, let me call it IB and BBH, with a t to the 1 minus 2 over d. So they have like, they can do it in any dimension. That's the result. They have a nice rational formula for IBBH. The paper is beautiful in the sense of it's, I think, very sophisticated, based on Donsker-Varadan. And let me just draw you the key thing. The key thing is that if I draw in terms of B, the rate function in dimension 5 and more, and now the problem can be solved also in dimension 4 or whatever, at some point, there is a plateau. So there is a B, let's say, critical, after which the rate function reach a plateau. And so the conjecture that if they could replace, I mean, that the two limit would exchange, that the limit when B goes to infinity and T goes to infinity that they treated, so this is BBH, would be the same as when you do that. You first take B to infinity, so you look at the infinite range problem, and this is really the problem that Kesten first looked, and Hanin, Mazel, Schlossman, Sinai solved. That's their conjecture. And let's say that, so the paper is, does not study the scenario, but they made popular a Swiss cheese picture. So they came up with this popular picture that they call the Swiss cheese, which is that based on their study and on the rate function and on its variational formula, they know, or it suggests that the two walks, actually independently would localize in a ball of volume. So the ball has volume T during a time of order T. So producing a density, so that this is my density of occupation of order 1. So let me draw you the two walk. You start at 0. First one is here, and there is a center that no one controls, where the walk is going to localize enough time, and then so that the density approaches inside this ball of radius. So the radius is T to the 1 over D, so that the volume is T. And the other walk is doing the same thing. Inside, you have a localization. And then that's it. So this is what they call the Swiss cheese picture. Why Swiss cheese? Because if the density is 1, it means that you make holes of order. There are holes of order 1 inside this ball of volume T. This was some heuristics, but they had no mathematical statement for that. And up to, let's say, so it's an old problem, 2000, and there was no other progress on that. So let me now tell you our results. I'm not going to make too many parentheses unless you ask me, but let me tell our results with Bruno and myself of 2020. So we can do the infinite time horizon, and indeed what we say is exactly that BBH were right. So we find the correct constant as the conjecture. So they were correct. But besides that, we have some information on this picture, which is that, so the statement is a little bit long because it's a conditional statement. Knowing that you have an intersection of, let's say, high T or value T, then for any epsilon, because I'm going to lose some mass outside this, let's say, ball of volume T, whatever epsilon, there is a scale which I can scale this ball, so that my first range intersection, my second range intersection, let's say a ball of radius L epsilon T to the 1 over D, bigger than, I'm losing just one epsilon. 1 minus epsilon T goes to 1. And I'm not controlling the center of this box, of this ball. It can be very far, actually. So I have to add something. I have to add that exists a center such that my ball has to be centered by X. And now the statement is correct. Okay, so that's by no way closing the problem, in the sense of that you have a very rough description of this Swiss cheese picture. And we hope, I mean, so it's just a first step. Let me emphasize that this is a first or a second step, because BBHT, the first step, let's say a second step. But by no way the last one in describing the Swiss cheese picture. Okay. So any question about the shape of this result? Going to, and you see, this does not convey really does not explain why you should have a Swiss cheese or anything like that. So before telling you why we could reach an infinite time horizon, let me just let everybody feel confident with this picture, derive heuristically this picture. And this should be simple unless I make a mess. So let me do the heuristics.
Sorry, I have a question. Is the upper or lower bound in A much easier than the other? I imagine if you have the picture of the Swiss cheese in mind, the lower bound could be slightly easier.
Yeah, the lower bound is already contained into Bolthausen BBH. Okay, because I think the lower, now I don't have it clearly, but the lower bound, I guess, so here, what about the lower? My remembering is that the lower bound was really a consequence of BBH. Not sure. This is obvious because you have an infinite time. So if you do it in an infinite time, no, it's not, doesn't go in this direction. Okay, so no, it's not that, it's not direct, but let's say it should be easy just because we are really transient in a transient regime. So let me, I'm not going to answer right away to your question, but let me say that the lower bound are easy and lower bound are consequence of BBH.
Thanks.
And really, I only focused on the upper bound. I would have to think a little bit why it's immediate, but let me go to a description of the heuristics, which is also a type of describing a strategy. So, so in the heuristics, you assume that the two walks, almost kind of independently, stayed a time tau in a volume V. And let's say it's a ball, but for the moment you just say that it's volume V. And you want to know what's this time and what's V. And I'm assuming actually, I'm trying to do the heuristics for a finite time horizon. So I'm looking really at Rn, intersection of RT tilde n bigger than t, and I'm assuming okay, n large enough, and we will see how large it is, and I want to find tau, and I want to find v, and explain how the Swiss cheese pops up right away. So the first thing is that if you stay at time t inside this ball, the density is the number of monomers you have inside the ball over the volume. And I don't need it to be larger than 1, because I'm looking at the intersection of the range. And what I need is that, so that's the key thing, is that the cost of doing that, the cost of localizing a walk at time t in a volume v, is exponential minus the time over the radius square. So let me write it this way. Okay, and I want the largest, I want the scenario which makes the largest probability of happening. So I want the super of this probability, which is basically that I have to look at the inf of tau over v to the 2 over d. So now transform everything in terms of density. I have to say that my constraint, my intersection bigger than t, just means that the 2 walk, so 1 walk spends a time tau, and in each of the sites it visits, there is a chance rho that there is another monomer of the other walk. So this is the intersection that they make, 2 times rho, and this must be of order t. Okay, so morally, my event is the fact that t times rho is t. So now let's just write tau over v to the 2 over d in terms of rho and t. So tau is t over rho.
Amine?
Yes.
So shouldn't you have rho square here?
One spend the time tau inside, and in each step it has a chance rho to hit the other particle. Time tau time rho.
Yeah,
That's
okay.
rho square.
Yeah,
but
okay.
t itself.
Yes, the volume times rho square. Okay, but then the sites can be occupied several times. So shouldn't you divide by g of 0 or something like that?
Yeah, I'm not looking at density larger than rho. You're right. It could be much larger than that, but I'm not. I'm thinking that they are not going to be interested in spending more time than just visiting once the sites, but they are going to be visited. Okay. So, and therefore tau is t over rho, and v is tau over rho, but tau is t over rho, so it's a t over rho square to the 2 over d. So when you write that, you find that it's t to the 1 minus 2 over d, and you have rho to the 4 over d minus 1. So I write it this one, 4 over d minus 1. And the parameter you can play with is rho. And what you are assuming is d bigger or equal to 5. So in this case, this is less than 1, and the infimum is reached when rho is largest. So the infimum is when rho, let's say, is largest, is 1. So what you find by this very simple heuristics is that then tau should be v, so that the density is rho, and all those numbers are t. So this is true only if n is bigger than t. You need a time n to be at least t. You remember I looked at the finite horizon problem, or n So as soon as n is large enough, it disappears completely from my heuristics. And indeed, you find basically that the picture of BBH is correct. By the way, you see also that in dimension 4, density disappears. So d = 4 is critical, and we have a problem in finding the correct scenarios for this finite time horizon. Okay, but in dimension 5 and more, it makes sense that, well, that's why the Swiss cheese picture holds. Modulo what Hubert was saying and things like that. That's the simplest heuristics I can propose. Both are in the same volume, but the same amount of time, and so on. Okay.
But okay, so if you make the computation, I don't know, if you do a bit, if you add some ingredients in the heuristic, can you get the exact density that you should get? Or because I guess it's not okay, there are some holes, so the density that you obtain is not 1, right?
Yeah.
But do you have the exact, is there an exact theoretical expression for rho, or?
I don't know if that's a good point. So on a scale t to the 1/d, where you must have something like that, and it doesn't go to 0. There's some always. I try to draw you the occupation density. It's not the constant, it's not, so if you had in mind that this would be something like that and 0 outside, that's not the case. There is no minimizer in their variational formula. So there is mass leaking to infinity outside this scale t to the 1/d. But I don't know if, I mean, they have a lot of information about the variational formula.
So the density in the end you get is it's not uniform. Yeah.
No. And we don't get
the compact.
You see, you will see in the strategy we use is that we use their information in finite time to show that everything happens in one ball, but we don't get more information than they have. We use their result. It's crucial, and I'm not getting more precision on their density. On the density it should be. Okay, so that, I mean, the good thing is that, as I said, it's just a second step. Many things are missing, and they are also missing in a finite time horizon. But okay. Okay, so that was about the heuristics. Let me say what maybe were the difficulties. And one thing is that we can understand quite easily is that since you are in infinite time horizon, there are so many places where the random walk can meet. And the problem, there is a combinatorial problem, is just from the fact that there are so many places where two walks can meet. And maybe to make it more precise, I would say that there is some difficulty. Well, let me not repeat difficulty. The problem is to get rid of places where, or contribution where both densities are small. And I like to write this, they meet, but in a place where they have a small density. And this posed a problem, basically a problem. let me say, I mean, it's the same difficulty that I'm saying in a different ways. And the way I understand it better is at which scale can you probe folding of a random walk? So I introduced, I'm saying I understand it best, but I introduced a way that no one understands, words that no one understands folding. So let me explain a little bit what I mean by that and what is our contribution. So folding just means that the work is going to spend more time than typical. Okay, so let me first go say what's a typical random, what a typical random walk is doing. It starts at 0, or something like that. Imagine that's not okay. You take a site which is visited. You draw a ball of radius r, and you ask yourself, what's the density? How many not particles, but how many monomers? How many position of the walk are inside this ball? And so typically there are r² sites inside this volume Rd. So the typical density is 1 over Rd minus 2. And you see that the random walk is really something which changes as you change the radius. So it's not a homogeneous Poisson point process or anything like that. So the density, the correct thing is that the density time R to the d minus 2 is of order 1. So the density depends on R. So folding just means that I'm going to take, let's say, scenarios or places or sites where the density time R to the d minus 2 is much larger than 1. That's for me what means. That's going to be a definition of folding. So let me make it more precise. This was for one site, but I can divide. I'm going to color, and this is something that I think Pablo will like, is that I'm going to color the range according to density. So my colors are, my palette of colors are going to be the value of the density, that I have to link it with a scale. That's the scale at which I'm going to probe density. And what is that? It's all the sites less than n. And you might think I'm cheating. No, I didn't. Because I say that the whole thing is in infinite time horizon, but then I'm always limiting my work to a finite time horizon. And you will see that that's an important issue. So I'm coloring the range. I'm taking only the monomers or the labels such that around them, when I take a ball of radius r, the intersection with the range up to time n is bigger than the row I chose. Saying that this is a place where folding occurs if I choose rho and r bigger than r square. R square is the time you would spend for a classical random walk, typical random walk. So if this is larger than r square, this is folding. And our hammer, the estimate we use over and over, is we know how to estimate this, the size of this set. So now you have to think that your range, the range of one random walk is going to be colored according to density. And so the colors are just according to that. Ri are going to be chosen accordingly. I have to tell you how. And let's say that our hammer is the following estimates. If the density times r to the d minus 2, instead of being just what I said, larger than 1, I have to be more precise, is bigger than c times log n, and n is this length of the trajectory, then the probability that the colored region, according to rho, is bigger than L, I have a bound. Exponential minus L to the 1 minus 2 over D and rho to the 2 over D. And a constant kappa. And it's an upper bound. I'm only thinking about upper bound. So and so you might think that this is weird or ununderstandable, but this is exactly a localization event. So you can think of it as, it means that you spend a time t in a region of radius r. And this can be written in this way if you accept that. So the time is the number of monomers. I have L of them. And the volume is that these monomers are at a density rho. So they are at a distance, each one from each other, like the volume is L over rho to the square, 2 over D. So this will give you the correct scaling. So it's just a localization event. But the key thing is that this was missing. This is how far we can go in probing what a folding event is for a random walk. Now, you might think, what is this n? The whole problem was an infinite time horizon. So n actually is going to be very large in the first step. Is length or a time or length after which two random walk cannot meet in my large deviation scale. So let me be more precise. Imagine I'm asking you the probability that two infinite random walk meet outside a ball of radius r. What do you have to do? You have to just do sum the green function square for all the x's bigger than r. The complement. This is the complement of the ball. I'm asking, is it possible that two random walk independent meet outside of BR? You sum that, and just because if what I said is correct, you should have something like that. So you could take R big enough such that this is much smaller than exponential minus big constant times t to the 1 minus 2 over d. So R, you can localize your everything which happened in a huge box. And this also means that after a time like R square, they won't meet anymore in your large deviation scale. So n, this n, you can always take it to be, let's say, the square, but it doesn't matter, beta large to the t1 minus 2 over d. So this is a huge volume, so it doesn't reduce the complexity of the infinite volume. I'm just saying that I can, even if I'm doing an infinite time horizon, I can stop the time at a huge exponential to the t to the 1 minus 2 over d ball. But then what is my condition on which I can probe? The condition that I was telling you about was saying that if the density time the radius to the d minus 2 is bigger than how much log n, and here I'm going to plug this log n t, then I can control the size of my, let's say, high density level sets. And the miracle, so there is a small miracle which makes us lucky here. It is that if you take the Swiss cheese means that everything happens in a density 1, in a scale r to the t to 1 over d. What do you discover? That one time, let's say, t to the 1 over d or a given constant is indeed larger than the log of that, which is, oh, I did a mistake, I have to take to the power d minus 2. That's exactly the same thing on this side. Let me take a big constant here. So what is this miracle? It is that we are lucky enough so that our condition is good enough to catch the Swiss cheese picture. Just because we took a huge volume, but its log is exactly the right thing so that we can bound the level set or the occupation, the high density occupation of one random walk. So that is such a thing. In the sense of if we had a log square here, we would not have been able to solve this problem. So there is something in our condition which is optimal. So I go back into our hammer. This is an optimal condition, the log. And okay, so which also we obtained recently, actually, the same year, 2 years ago, and which allows us to not only to color a random walk, but to say what is the probability that each colored region has such a volume. So we have, we take one random walk, we color its range, and we have, so this is low density, this is high density, and we know what's the volume, bounds on the volume of each colored region. And then the other nice feature of this problem is that this problem is exactly that one transient random walk lives into a colored landscape made by the density of the other random walk. So I have, this is my first random walk, S, but what do I have to do with S? I just have to intersect it with another random walk. So I'm imagining instead of the intersection, I take the time spent by the other random walk in a given region, in the region of high density. And I'm asking, is it easy to know what's the probability that the other one spends a given time in a given region? And I say, yes, of course, that's elementary. Why? Because I have a transient random walk. I can you fix the red region. And we know what's its volume because of what I said, because of our hammer. So now the occupation by one random walk of a region is just bounded by a geometric random variable. Transient random walk is going to come a few times to V and then go away. So you only need to know the expected value of the time spent in V. So this is the bound if it were really a geometric random variable, T over its expected value, expected time spent by the other one. And I'm fixing V. V is, the color now are fixed. And what is the expectation of the time spent in a region? This is the green function of V is fixed, we fix V, and this is just the green function of V, that is the sum of all the sides of V. But this is the expected time spent by a random walk in a region V. If the region V is a region of density, let's say the sides are at the density rho, red rho, then it's easy to see that this is rho time the radius square of a ball of equivalent volume. So it's V to the 2 over D. So that's a standard stupid estimate of the green function, or also always less than if it was a ball that you were visiting, and the sides are far apart if the density is small. So that's how you get this is how you get estimates on the probability the other walk spends in a colored environment. So now there is really nothing to do. According to the density, you will use your hammer. You have a bound on V. So V is bounded by the hammer estimates. Something depending on rho. Let's say T over some rho to a given power. Then you have this bounds, which tells you which density you can forget. If this is less than t to the 2 over d, you can forget about it. So in this way, we could get rid of all the low density values. So it's really elementary. This is a one-line computation, just using the fact that it's a Markov process. The hammer. So let me tell you what everything boils down. All these folding problems at the end have the same issues that has to be solved. It is to understand what's the probability that a random walk folds. By folding, I mean spend a normal time in some balls of some scales. So all the balls are of radius r. You have k of them. You don't know where they are. You just know that one walk has this volume, but you don't know the shape of the random. This is a random distribution of centers. And that's why I need that the walk is in finite time, so that I know at least that they are all between minus n and n to the d, if the walk lives up to time Sn, let's say. So all those problems requires you to understand this quantity, and which is a classical quantity, the probability that a random walk visit uniformly some region, but the region is random. So the big issue that we always have to face is that. So now it's kind of simple because the centers, they can be anywhere. So you have this volume to the power number of centers. And then if you fix them, you can say that, okay, you're going to visit one, you spend some time, then the other one, etc. And what pops up is the capacity. So that's some new object, the capacity of this region. So the union over k of those ball of radius r centered at xi. So just a few words about capacity is that the capacity is just the way your domain looks like if you're far away. So you take a site far away, your domain is like that, let's say, and you ask what's the probability that if I start at z, you touch your domain lambda. So the capacity is this number. Okay, you have to normalize it by touching 0. Because it could be that you take z to infinity and you don't want this quantity to be finite. So that's the capacity. So it's the probability of hitting your domain from infinity in some sense. Okay, and this is really what comes up here. So what happened is that the capacity is always bigger than the only thing one has to know is that it's always bigger than the capacity of a ball with the same volume. So you have this bound. So here you have balls of radius r centered at k. So you have a volume k to the r to the d to the power 1 minus 2 over d. Unless I made a mistake, but what you see is that when you face such an issue, the real problem is that you have too many ways to put your centers. You have to the power k. Whereas what you gain from visiting those sites is a k to the 1 minus 2 over d. And that's problematic because when k is large, the combinatorial factor kills you. And the whole trick, so you see here, if I wanted to make the thing efficient, I would need to take rho to the r to the d minus 2 must be larger than the log n. The log n comes from this n here, time k to the power 2 over d. Here I have k, and here I have k to the 1 minus 2 over d. So the difference is that. And this inequality, I presented it 2 years ago in Buenos Aires. That was the best thing you could do at the time. But this is a bad thing. And the new ingredients, which is not really probabilistic, is the following fact that I want to end up with this fact. So it's a nice inequality. which we wrote in another paper, is the fact that in each set, V or whatever, there exists a subset which a work starting at infinity could not distinguish in a sense, but there is a subset much smaller. So the volume of U is like the capacity of V, which is much smaller, but whose capacity is the same, of the same order. So there are constants between them. So since hitting or uniformly visiting is just linked with the capacity, those two sets, U is a subset of U, will be seen the same way. So it's as easy to see or as hard to see one or the other. But in the U set, the nice thing is that it's much smaller, and so small that its volume is just like its capacity. And therefore, if you, instead of asking that the whole thing be seen, you take a subset, which is U, then you are gaining much more in combinatorial. I mean, you're losing in the combinatorial in a way that you can get rid of this K here. And therefore, you reach the scale at which you can attack the Swiss cheese problem. Okay, I think that's kind of optimal. And if I were, okay, I don't want to say more about, I hope this fact is clear enough. In each V finite in ZD, it's a subset of ZD, that exists a U inside V, such that U has the same capacity as V, so it's the same thing seen from infinity, but a much smaller volume. And the way to build U is a nice probabilistic way. From any site of V, V is the deterministic, you throw an independent random walk. If the random walk goes to infinity, keep it. If it returns to V, forget about the site, don't keep it. So I throw things independently, and I build a set where I keep only the sites which are exposed to infinity. And this set has exactly the correct capacity, the correct volume, and it's, much smaller. This gives us the optimal hammer to crush the problem. So let me say maybe in 1 minute that I want to say that this problem in a sense was too easy because I had two independent random walk. And so it was one moving in the landscape of the other one, but there is something where they have only one random walk, Rn. And so you take away its typical value and you ask to be smaller. So how does a random walk organize itself to have a small volume of the range? So it's an absolutely classical problem in probability, but I'm taking Cn much smaller than the typical value, much smaller than n, but also bigger than something because I don't want to go in the Gaussian regime. And this is open in dimension 3, but I'm interested in dimension 5 because I claim that here also you have a Swiss cheese on a scale zeta. And so this probability should be exponential minus some constant that I should know time zeta n to the 1 minus 2 over d. This is open. And this is open because we cannot go in the proper scale, in a sense. Second open problem, do the same thing with another process. What is, instead of one random walk, take a branching random walk. So what you take a Carlton-Watson tree, critical, Carlton-Watson. You take on each edge an increment on ZD. So you plunge it into ZD, ZD t bigger or equal to 5. And same thing about the range. I mean, you can ask yourself, what is, I would say the first thing to ask is really what I call our hammer, which is what is the probability that the branching random walk visit two balls a certain amount of time? You fix a time here, how much time it must visit, or a density row, and you try to obtain some estimate. And I'm curious to know what would play the role of the capacity, etc. So, and I'm sure Hubert will look at the self-avoiding random walk and try to get something like, what is the probability? You can ask the same thing about the intersection of two independent self-avoiding random walk in high dimension and try to get estimates about the tail. That's maybe the hardest, but branching random walk, I have to say we are making some progress with Bruno. And this I tried, the number one I tried with Maximilian Ischler. We are missing something, but it's still open, and it's surprising that it's still open. Okay, I think I went maybe over my time.
Thank you very much, Amine, for the nice talk. Is there any, let's thank Amine. Is there any question or comment?
Amine?
Yes.
Yes, Hubert.
I'm not hearing.
No, neither me.
You can't hear me?
Yes.
Now, yes.
Okay. So when you mean branching random walk, do you mean intersection of branching random walk?
Okay, so at the moment, yes, of course, you would you look at the range condition on surviving a time of having a size n, because I'm taking critical ones, so they will die. So you have to continue having a given size. So you call this n is going to be the range for the this tree condition to have n children, and yes, I would like to have something like that, but even the what is the chances that the volume be less than something? See the folding. What I'm interested in is folding of this branching random walk. I can tell you already that if you ask such a thing, imagine you take your branching tree, and you ask what's the probability that the branching thing spends a time t in a ball of radius r. That's not written in the literature. That's not known. So first step, this is something I needed actually. But then second step is take two balls and try to get this this probability. What's the probability that one branching random walk visit two balls a given amount of time or a given density? So this we have now. Let me write you the result. Upper and lower bound with some constant in dimension 5 and more. In dimension 4, something completely strange with the square root of t here. But this was for a ball. Then, well, you have to make some progress on that to be able to look at the real problem of the intersection of two ranges for your branching random walk. Yes.
Yes, thanks.
I have a question as well. I didn't see any place you specifically need ZD unless, you know, there are heat kernel estimates and volume estimates. Is it the case that everything said holds for a graph where you know the heat kernel estimates and growth of balls?
Okay, so I did not say that. You see, I just spoke about the first step, which was to get rid of low density out of the game. And this was a lot of scenarios that you can read right away with our method. But then there is, you reach a place where you have a few balls. And you have to go from a few balls to one ball where everything happened. And this place requires you the large deviation principle with the exact, we need to know, to have this constant here, to know that it's concave. So this requires the full work of BBH. So if we did not have their work, we could not go from a few balls to one ball where everything happens. So that's, I'm happy because that's, before I found their paper, it was very sophisticated, but it's actually very useful. I need this thing. So unless, so first step is on a graph, can you have a large deviation principle with their precision? The constant positive, but and concave speed. And then we can run our program with indeed very rough. This was very rough bound on green function. This was very rough, but this is very sophisticated. The one ball business or the large deviation in finite time is a sophisticated business, which requires a lot of very precise estimates, not just asymptotics.
I see. Thank you.
Created estimates, and it's a lot of work. This was a lot of work.
Okay. Are there any other questions? I just have a comment. One is what happened with loop erasing random walks? Would you have any idea? It's like the same as self-avoiding?
No, I think it's much simpler than self-avoiding. But you're right. It's a nice question for loop erased random walk. In dimension 5 and more, there is a way to define an infinite time horizon loop erased random walk, or so I don't have, I didn't try.
Okay.
I wouldn't say.
Yeah, because the loop eraser and the self-avoiding, they don't like to stay in a small ball. Because for the other, it's okay, it's a matter of entropy. For those, they are really rejected. So, but you expect anyway the same result. Is that it?
Let's say in high dimension 5 and more, even self-avoiding.
Okay, yes.
They look
like.
Though I would be curious to know if one can obtain this. You see, the density 1, the Swiss cheese thing, is not going to be the same thing. I don't think that you can put the self-avoiding into a density 1 business. But Berg might know better. But I think this is missing as well. This estimate of what is the probability of producing a density rho somewhere, even rho small. But I think the first step, indeed, I should have mentioned maybe 2 bis would be the loop erased random walk. At some point, I thought about that and maybe convinced myself it was not so hard or whatever. But now it's like 2 years since we did that. And I don't remember what's.
Yeah, and something that is I couldn't understand well is this nice set U that has the same capacity as the other set. At what point of the argument used it? After you decided that you have only one ball? No.
This is crucial in obtaining the optimal condition for what I call my hammer. To go up to log n, I really need to, in this estimate, to use that inside my set of centers, there is a subset much smaller. So it's really there. It's in this condition. Before I had such a lemma, but with a much worst condition. So here, that's where in the hammer you need this lemma about capacity. But it's you don't see it here. Capacity does not play any role here. Maybe you might feel that there's one over this capacity. It's really hidden in the probability that I said, that you have to visit uniformly something, a domain. There you see the capacity popping up. I should have mentioned that maybe a lot of progress are coming from the random interlacement, which was basically invented to understand the Swiss cheese picture, which is exactly that you have a density 1 actually for random walk. So there is a few remarks in the last paper of Sneedman about understanding the Swiss cheese. So I think that he's on his way to get a clearer picture of what is this domain of density 1 using random interlacement. So make precise this.
Thank you, Amine. Any other question or comment? Okay. Okay, so let's thank Amine again. And we see everybody next Wednesday. Thank you, Amine.
Okay, bye-bye.
Bye.